3, maybe 4 molecular modeling, you'd have to look at the syllabus, maybe 4 molecular modeling experiments this semester and a couple second semester. In any case, the first handout is a general introduction to molecular modeling. It was written a number of years ago, mainly to introduce people who have never done any molecular modeling to the concept of molecular modeling. We'll go over some of those concepts now. And then you've got a molecular modeling experiment on alkanes and cycloalkanes. Most of the molecular modeling experiments will have an introduction that talks a little bit about the theory that's relevant to what we're doing at a particular time. It will then have a step-by-step how you build the molecules, how you do a calculation, that sort of thing. And then it'll have 2 to 3 pages of where you can enter data that you record from the computer. And it also will have some questions for you to answer. It is important to read through, it's like the GC, but even worse. It's important to read carefully the instructions. You're going to be working as partners. You need to sign up for a time. It will take you maybe an hour and a half to do a molecular modeling experiment. So I would say sign up for a time, and I've got to get a sign-up sheet over there, on your lab day, because we've only got 6, I think there's 6 machines over there, 5 or 6 machines over there that have Spark. Okay, so not everybody can get in there all at once. So sign up for either 1 o'clock or 2:30. 3 o'clock, you'd be sure they're out, but that only gives you an hour up to 4 o'clock, although you're welcome to stay longer. And if something happens that a machine goes down or you can't get in or whatever, come in some other morning. There will be organickers in there Tuesday, Wednesday, Thursday, Friday afternoon. So, if you have not done the GC, then you also need to do the GC work. How long is it taking you on the GC when it works? How long is it taking you on the GC? About a half hour to do your samples? Yeah, so it's, not. Okay, this is just what this is all about. Modeling. Airplanes fly. This is prop driven. Different levels of models. This one will kind of show, it's got wheels on it and it kind of runs along the ground, and then it's got those whatevers, and you can get some kind of an idea of what an airplane does. This one is much more detailed. Shows a lot more of the detail of it. It's more expensive. Maybe takes longer to master and interpret information, but you get a better picture of what it is. And then this one, I don't know if you can see, it is one of those that you fly with remote control, and it's actually got a motor in it, and the thing actually gets off the ground and does its thing. Much more expensive, much more complicated to operate, but the answers that you get as you move across here in terms of how does the real system operate, you get better and better answers. But it costs you more in terms of time and learning curve and effort to figure out what's going on. Probably costs you more money in order to develop the model. If all you needed to know was that an airplane has these long things on the side and then that thing in the back and some wheels, and it kind of will glide across here, and maybe I could have put one of those little balsa wood, they still make those things, balsa wood, where you throw it, am Am I speaking Greek, or have you ever had one?
I think that's fantastic.
They still work? Do they still sell them? No, they don't sell this little balsa wood airplane that all you have to do is throw it and it zips and you tip the wings and it...
No.
Well, anyway, we could have put that one in, I guess, if we wanted to, maybe at this point instead, but you wouldn't have known what it was, I guess. Same thing is true for molecules. We've got these real things that are molecules. They do all kinds of really neat stuff. And we would like a model that predicts what it does. Okay. We've got this. Lewis structures, which are rooted in what's known as valence bond theory. Valence electrons are important and determine chemical reactions. And we will learn to be able to look at these types of structures. That's a polarized bond. That thing tends to come off. There's electrons. That's a source of high electron density. Probably is going to be important in terms of reactions of this substance. We'll learn a lot about that. We're working with valence bond theory. Bonds are shown in the structure. Valence electrons are important. We also call these localized bond structures. Operates in the localized bond theory, then electrons are localized in this simplified model of the molecule, are localized between pairs of atoms or on an atom. So we'll spend a lot of time playing with this, modifying it, getting basic understanding such that when we look at an oxygen, we know it's highly electronegative, et cetera, et cetera. And from that, be able to predict reactions and picture those reactions and that sort of thing. Predict properties of the molecule. All right, that's a very simplified model. All you really need is a piece of paper and a pencil and some fundamentals, and it will tell you something about the way real molecules work. We can go to a more sophisticated model. It's not one that you will find used very much around here, but it's called molecular mechanics. It describes this arrangement of atoms which have a positive charge associated with them in some sort of fashion and a negative charge associated with them in some sort of fashion and a mass associated with them. And they are tied together with springs that operate under classical Newtonian, Isaac Newton, classical mechanics. Here is the molecule ethene that is being pictured. And we can make predictions from this using simple mathematical equations, simple Newton classical mechanics to make predictions about the behavior of a molecule. This model, however, really does not know much about electrons and how electrons operate in the presence of a nucleus. But the calculations are easy to do because they use simple equations, simple classical equations, classical physics equations. So you can get some predictions out of it, but they really don't know a whole lot about real molecules. But you can get predictions from this that's much better than what you can predict from this. And it's quick and easy to run on a computer, but you need a computer to be able to do this. When you get lots and lots and lots of atoms, as you would have in a protein, say in an enzyme or something like this, that type of model will work nicely. So a lot of drug design for example, looking at how a drug interacts with an enzyme to block it as an inhibitor. A lot of those calculations will use molecular mechanics because it's simple mathematics, so you can deal with a molecule that's got hundreds, thousands of atoms in it and do a reasonably decent job of calculating some of its properties. But doesn't really know about how real molecules behave in terms of electrons. You have to go to quantum mechanical models. And there are two levels of quantum mechanical models: semi-empirical, which is a somewhat simpler one, and what's called ab initio, from the beginning. That is much more complicated, but it can give you sophisticated structures of molecules with the surface of the molecule and how that surface feels, in a sense, from an electronic standpoint. So you can get very good information about how molecules behave. It requires a fairly sophisticated computer program to be able to deal with these types of calculations. The calculations tend to be very long, or much longer anyway, with this type of calculation than with semi-empirical. But the data you get out is much better in terms of predicting all kinds of sophisticated properties about molecules. We'll spend most of our time here with semi-empirical calculations. And the types of calculations are like AM1 and PM3 are the names of these types of calculations. I think Spartan now uses PM3 as its semi-empirical method. In any case, the instructions will tell you what type of calculation to use. It may vary from experiment to experiment, so make sure that you know which type of calculation you're going to be using, because you'll have to tell that to Spartan. Okay? So let's see what else we got here. Well, this is showing us molecular mechanics, and molecular mechanics is essentially, remember this is Newtonian, it's essentially calculating the energy of a molecule, and it's doing it by looking at the bond and saying, well, the bond's this vibrating thing, so it's looking at each one of the bonds. It's looking at angles, like that 109.5, and maybe varying it somewhat. It's looking at what we call dihedral angles. If you had 4 atoms bonded to one another, and you look down this bond, look right down that bond, such that atom's behind that atom, you're going to see these 2 lines. And as you rotate about this, you'll be changing what's called the dihedral angle, because from the perspective of looking down this bond, you only see 2 lines that make an angle. So as you rotate about that bond such that that would come around, you'd have what's called a dihedral angle, and that's what this term is looking at. It's also called torsions. And then here are the 2 things that we talked about before, which are non-bonded interactions. Okay, and they can be intermolecular or intramolecular, but this is the one that is the Coulombic, the electrostatic thing. You can see here we're calculating force, not energy, because it'll be linear with regard to energy. And up here we have that Morse curve with the attractive term and the repulsive term. And I think I mentioned Lennard-Jones 612 potential. That's a Lennard-Jones 612 potential right there. Okay, it's an exponential term. That's the way molecular mechanics looks at a molecule. It's doing things that are associated with the bonded nature of the molecule, and then it's doing things that are associated with non-bonded forces in the molecule. It could also take 2 separate molecules it would have already calculated this, but it could then calculate the non-bonded interaction between two molecules. And molecular mechanics calculations can do that for us. That's sort of the way molecular mechanics operates. The more sophisticated is, oh, well, that's just something that I threw in for myself that well, let's not bother with that. Well, I guess it can't hurt to say it. For example, in that bond that molecular mechanics is calculating, it's calculating it this way, with a harmonic function, a quadratic function, x squared plus a, or something like that, or x plus a squared, or x minus a squared, quadratic type thing, second power equation once you multiply it out. It gives a function that looks like that. It's an approximation. This is the way a bond really behaves. By the way, that kind of looks like the non-bonded interaction, doesn't it? Same type of curve, which is called a Morse curve. But that one was just, oh, that's really a cool diagram of have a nice Morse curve compared to a harmonic oscillator type. And you can see that the harmonic oscillator does underestimates when the attraction comes in and underestimates, whoa, how much pain you get with that if it was non-bonded with that steric interaction. It tends to fall to the left of the actual in both cases. But that's just kind of you don't have this, it's not in your handouts. If you want, geez, I wish we had just one website or one Blackboard. But I could post that under course documents if you decide that you want to see this. Quantum mechanics, two different levels, semi-empirical, ab initio. This requires a different type of approach for us to sort of grasp what's going on here. This, beyond quantum mechanical, which says they're discrete levels, this is what's referred to as molecular orbital theory. Molecular orbital theory. You start with atomic orbitals on an atom in a molecule. Each atom in the molecule has atomic orbitals. What you then do is you combine those atomic orbitals to make new orbitals, all of them, on all the atoms, to make new orbitals that encompass the entire molecule. And that gives you a ladder of molecular orbitals. And then you fill that ladder the same way you filled the ladder, the electron configuration diagram. Those electronic levels on an atom, you fill them the same way. Put them in 2 by 2, fill them up as you go. Molecular orbitals, in a sense, are a little bit easier because they're singly degenerate for the most part. There's some compounds that are doubly degenerate, but they're in general singly degenerate, so it just looks like a ladder. Boom, 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 boom. There are no degenerate ones, two molecular orbitals that have the same energy. In most compounds, some compounds they do have degeneracy. But that's what you're trying to do, and maybe the next one. Oh well, this is a difference between semi-empirical and ab initio. Semi-empirical deals, without going into a whole lot of detail, semi-empirical deals primarily with tinkering with the atomic orbitals that are in the valence shell of the various atoms that are involved. Whereas ab initio tinkers with all of them. And we could talk about what I mean by tinkering, which is really pretty complicated. But in any case, the main thing distinguish is how many electrons is the calculation, or orbitals that are associated with electrons, is the calculation actually struggling with. And it's only the valence shell electrons in semi-empirical. It's all of the electrons, including the buried shell electrons, that ab initio is trying to deal with. And so consequently, these calculations are much faster than those calculations. But these are the best calculations. These will give you the best results if you do ab initio type calculations. So we've got basically, as far as Spartan is concerned, three what are referred to as levels of theory. One, molecular mechanics. Very simple, very fast, crude results. Doesn't know about electronic properties of molecules. Two, quantum mechanical types. Semi-empirical. Slower than molecular mechanics. Does give you fairly useful results. Does know about electronic properties of molecules. But not as precise answers as you could possibly get. And then the very slowest but very best, ab initio calculation. Two quantum mechanical types, one molecular mechanics type. If you've done any crude cleanup, you build a structure and you tell it to, what do they call it? It's something like minimize it or whatever. It will do a quick and dirty, because it does it, boom, just like that. I mean, 2 seconds and your structure just changes a little bit. That's a molecular mechanics calculation that's done in the background that you don't even realize what's going on. But that's what happens there. And then you go on, because most of our calculations are going to be right here. Semi-empirical. They'll be fast, they'll give us useful results, but not the best results you could possibly get. Just to sort of help you understand molecular orbitals and relationship to atomic orbitals. Hopefully, you are familiar with the concept that you can take atomic orbitals, which have certain electron distributions associated with them, where an electron can be in an atomic orbital. And then you do, although I don't think I used the phrase, a linear combination of those atomic orbitals, LCAO. I did say you add together the 4 equations. Well, that's linear. If you're adding the things together, it's linear. To get new orbitals that have different shapes from the atomic orbitals that went in, point into different regions of space around the nucleus than the atomic orbitals do. Okay. That was hybridization. So you're familiar with that general concept of taking atomic orbitals, doing a linear combination of them to get some new orbitals, and those new orbitals occupy different regions of space from each other and from the original atomic orbitals that come together, that were combined, right? So you're familiar with that concept. Linear combination, LCAO-MO, linear combination of atomic orbitals to produce molecular orbitals, is in principle doing the same kind of thing, except instead of limiting it, as we did here, to combining atomic orbitals on a particular atom to get some new kind of orbital, a hybrid orbital. Now we're combining all the atomic orbitals on all the atoms in the molecule to form molecular orbitals that extend, in principle, to encompass the entire molecule. but they'll vary as to where those molecular orbitals are in the atom, in the molecule. And this is kind of showing it's sort of a very simple molecule that you know about, that's water. But what we've done is we've taken the 1s orbitals of those two hydrogens and the up through 2p orbitals, atomic orbitals, on the oxygen, combined all of them, and gotten, and this, the lines aren't there so that you can see the structures, but a ladder of energies of molecular orbitals that extend in different areas of the molecule. And since this is a symmetrical molecule, where you see the density of these various molecular orbitals is symmetrical. But if you've got a larger molecule, you might find, no, there's practically nothing way out there in that part of the molecule. Molecular orbitals from atomic orbitals. So molecular orbital theory, that should help you get some sort of grasp of how molecular orbital theory is working and how molecular orbitals operate, since you have a feeling already for hybridized orbitals. Let's see what else we've got. This is more detailed than you probably want to know about atomic orbitals and molecular orbital theory. But atomic orbitals have a fairly, the profile for the what's the best way of saying it? For the variation of the energy of the system as the electron moves relative to the nucleus, have very complicated energy versus distance relationships, profiles, graphs. When we square that, we get these shapes, spherical, the p orbital, and whatever. Those equations are very complicated. And so what, what the computer does is it takes a combination of Gaussian functions. That's a Gaussian function, Gaussian distribution. Normal distribution for grades in a course, that sort of thing. It's a Gaussian type distribution. And it takes a number of those and combines them in order to make something, a mathematical function, that approximates how the energy varies with distance from the nucleus, depending upon what kind of orbital that you're looking at. It can get pretty complicated. But these numbers are simply saying, and this is for an ab initio calculation now. So it's dealing with all the electrons. But it kind of gives you a general idea of how both semi-empirical as well as ab initio is operating. This is how many of these things it uses to construct an energy profile for a buried shell electron. So it takes 3 of those. It then does, this is for the valence shell orbitals, and it essentially makes 2 orbitals out of it, like this and that, using Gaussian functions to make this. And so it gets 2 orbitals to approximate 1 orbital. And it weights those. You know, how much does that big one, where the electron is farther away from the nucleus, contribute to this new orbital that I'm trying to make it look like a p orbital on a carbon, or a p orbital, in this case anyway, or a p orbital on a nitrogen. Now, they ought to kind of look like one another, but a nitrogen's much more electronegative than a carbon is, so that p orbital, valence shell, p orbital, of a nitrogen ought to kind of look like that on a carbon, but geez, it's got much more positive charge in the nucleus, so it ought to pull them down more. That's what this is doing, and it's called a split basis, a split function basis set that we're dealing with. It allows orbitals to get bigger or smaller. And this is how it is doing it. And the bigger these numbers are, the more sophisticated these orbitals are. But this allows bigger or smaller of the same type shape orbital to be approximating a mathematical function, to be approximating what the real orbital behaves like. But it's still symmetrical about the nucleus. If I'm bonded to some atom next door that's pulling my electron density away from me, my cloud isn't going to be symmetrical, it's going to be tipped over. And so if you see a star in here, what they've done is they've taken like a p orbital that I've been playing this way with, and then mix in something like that, which is a d orbital. And wherever green and red overlap, they cancel each other. Wherever red and red overlap or green and green overlap, they reinforce one another. And what you can see is it skews the orbital. This is much more the way orbitals actually behave. They can get bigger or smaller depending on what the nucleus is. They can be off-center depending upon who I'm attached to. These are getting more and more sophisticated, longer calculations, but more and more sophisticated to predict the way the orbitals actually look on an atom of a particular type in a molecule. And then once I've got those atomic orbitals, then I put them together to make molecular orbitals. So there's a lot of this stuff going on to get the atomic orbitals on an atom right, and then we'll begin to blend them together like we did with hybridized orbitals. So it's a very sophisticated type calculation that we're dealing with, but they get more and more complicated. The bottom line is, the bigger these numbers are, the better the calculation is, but the longer the calculation is. And if you got that little star, it's even better, but again, it's longer calculation. Without going into any more detail, that will tell you something about when you click on this type, and these are ab initio ones. When you click on this type, it's going to be quick and dirty relative to this one. But the results are going to be much better with this one than they will with that one. Without going into a whole lot of detail, and there are a whole bunch of these different ones, and in some cases you even have 3 numbers in here. 3 numbers here. So you use 3 orbitals to do all kinds of stuff. Oh, enough of that, but just so you have some kind of feel of what the heck's going on here in my calculation. Now, I've got my molecular orbitals. The computer has sweated bullets. It's now got molecular orbitals for my molecule. I have put in my molecule. I've told Spartan, here's the molecule I want to calculate. Now, when you do that, what you're doing is you're saying, here are all the atoms, and here's where I think they ought to be in space relative to one another. And it will figure out what the bonds are between them. It'll figure that out. And from your valency and all that sort of stuff and how close you put them. So I have put in a structure with a certain number of atoms, certain arrangement of those atoms relative to one another in space, certain number of electrons. So it's got this number of electrons, and that's just by charge. So you don't have to tell it how many electrons each atom brings in. If you say the charge is 0, it's going to say how many electrons does that atom have. That's how many it throws into the pot. And you've thrown in some sort of a geometry with it. Now, this bond is really too long. But that's the way I happen to build it. Maybe I want to know the energy of that thing. There are two types of calculations we can then do after I've put in the input geometry of my molecule. I can do what's called a single point calculation. And what the computer is going to do is say, okay, you have frozen those atoms in space. You've told me how many electrons there are. I'm going to go play, and I'm going to calculate for you what the energy of that molecule is just as it is. A single point calculation. In some cases, you want that. In some cases, you want a single point calculation. In other cases, and in fact, in most cases, you're going to say, well, I kind of got it reasonably close, just so you can kind of get that thing there. Why don't you, computer, now go move those atoms around just a little, each one just a little bit, and what happens to the energy each time I move one? If the energy's going down, well, keep them moving that way. Oh, yeah, it'll, okay, I'm going to move this oxygen a little bit. Oh, the energy gets better. Oh, that's great. And it'll keep moving it, and the energy will get better and better. And by that I mean it will be a more and more negative number. And that's a critical thing to remember, that these energies should be negative values, and the more negative, the more stable the structure is. It will be doing, if you tell it to, a geometry optimization. It's moving the atoms around, trying to find an arrangement of those atoms that has the minimum energy for the molecule. And that's called a geometry optimization on a calculation. Most of our calculations will be geometry optimization types of calculations. Another thing to remember, see, maybe we started up here at that A prime. And it starts to move my atoms around, and the energy of the system drops. When it hits a certain point, that would be that A, for example, it finds, okay, I've been sitting here for 20 minutes doing a little tiny movement of this atom and that atom and that atom, and the energy is not changing much more at all. I quit. There's your result. It has hit the optimized geometry. Maybe that's not the most stable geometry of that molecule. I'm not talking about hand grenading the molecule, as throwing all the nuclei and the electrons totally apart and let them come together to the most stable arrangement, like that alcohol versus the ether that we first started with, two things that had the same molecular formula but different connective structures. It's not doing that. It's not changing the connective structure. It's just trying to change bond distances, bond angles, dihedral angles to get a minimum energy for the thing. This is what's called a local minimum. Because of the way the computer operates,